Okay, so let's take those ideas of average rate of change and relate it to instantaneous rate of change as we get to a definition of derivative. So to start with the idea of average rate of change and our secant line. So again, the secant line takes two coordinates on our function, covering a span of x values. And what we're doing is looking at the line between those 2 points. So that right there is a secant line, and we have it going through two coordinates, and with that we can estimate an average rate of change over values of x. So the secant line is the line okay, I've just said that a few times for you. So AROC stands for average rate of change. Let's get that written down as we see AROC going around. Average rate of change over A to B. And what we do is we look at the difference in outputs over the difference in inputs. We also talked about how we could use a difference quotient, looking from a value of x to x plus h, and evaluating that could also give us an average rate of change. And the difference being, just to make this clear, so like here we're looking from -1 to +2. So using this AROC formula, we would be looking at the interval -1 to +2. And for the difference quotient, we would be looking from -1, and then we want the equivalent to +2 by going -1 plus 3. So we would use a value of h that is equal to 3 for this calculation. Okay, so there's our average rate of change, but instantaneous, we're looking at just a single point, and we're thinking about our tangent line through that point. So a line that matches the slope just at that coordinate as best we can. That's not a great drawing, but we intersect at that coordinate and that coordinate only, and we're trying to match the rate of change at that instant on our graph. So the tangent line goes through one coordinate on the function and is the slope matching the function at that point. The slope of the tangent line over x to x plus h, where h is approaching 0. So again, this idea of getting closer and closer to x without equaling x is the instantaneous rate of change. And right here is our formula for calculating that slope of the tangent line, which we saw in that last video on the pre-lesson of getting instantaneous velocity. Okay, so let's get some definitions and some new notation here. So the derivative, and we can call this also slope of the tangent line. We can also call this instantaneous rate of change. All of these mean the same thing for us. Rate of change. So the derivative is the slope of the tangent line, is the instantaneous rate of change of our function. So some notation here. This first one could read out as f prime of x. It's also called the first derivative of f of x. dy dx also represents the first derivative of f of x, or the derivative of our equation y with respect to x is what that's showing. Let's write that down. Derivative of y with respect to x. So what that's telling us is what our output value is and what our input value is. M with a subscript of tangent is slope of the tangent line. So M for slope, and then TAN for tangent line. And all of that to say that we calculate it with this formula right here, that we're taking the limit as h approaches 0 of f of x plus h minus f of x all over h. So lots of different notation here that really comes from a history of different mathematicians discovering calculus at different times and using their own notation, and we've just kind of adopted all of them, and they have their different uses. So we'll see in some sections that we want to stick with the notation that Newton used, and sometimes we'll want to stick with the notation that Leibniz used, just because it makes the notation a bit clearer for the different instances. But you'll kind of see me, I'll probably stick to f prime of x quite a bit, but sometimes we'll want to use that dy dx as it'll be helpful, but it all represents the same thing. So let's get into some calculations here. So we have this function, 3x squared minus 4x plus 1, and I want to find f prime of 2, or the first derivative of f of x at x equals 2. So what I'm going to do is, to find f prime of 2, we're going to take the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. Now, I'm going to show you a few different ways to do that, and maybe I'll switch between these two equations. You can either do the calculation all together in the equation, or you can separate it up, which I find kind of keeps things organized and reduces errors. So let me show you kind of the separated way of doing it, and then the way of doing it all together. And let's go ahead, I'm just going to make a little line here to separate. So let's say I wanted to find f of 2 plus h. Well, that's going to come from 3 times 2 plus h squared minus 4 times 2 plus h plus 1. And what I'm going to do is off to the side here is just simplify. So that's going to be 3 times, so 2 plus h squared should be a 4 plus 4h plus h squared. I did not give myself nearly enough room over here, but we'll go with it. Minus 4 times 2, so minus 8, minus 4h plus 1. All right, distribute that 3 through, so a 12 plus 12h plus 3h squared. Negative 8 plus 1 is a negative 7, and then we have a minus 4h, and all of that's going to simplify down to 3h squared. 12h minus 4h is a plus 8h, and then 12 minus 7 for a plus 5. And what I'm going to do is take what we just found here and replace f of 2 plus h with that expression. So we're looking at the limit as h approaches 0 of 3h squared plus 8h plus 5 minus, and then I want to find f of 2. So f of 2 is going to be more straightforward because we're just plugging in a value. So for f of 2, we're looking at 3 times 2 squared minus 4 times 2 plus 1, which is a 12 minus 8 plus 1, so a 4 plus 1 is 5. So what we're going to do here is then substitute this value of 5 for f of 2. So I have subtraction as part of the format, minus 5 all over h. And now I can focus on just simplifying. I still can't plug in h equals 0 because of that h in the denominator. So I'm going to keep simplifying, which will leave us with a 3h squared plus 8h divided by h. And then I'm evaluating the limit as h approaches 0, and an h is going to cancel with each of the terms, so we'll have 3h plus 8. And now I'm at a spot where I can plug in h equals 0. So I'm going to have a 3 times 0 plus 8, which is 8. So all of that to show that f prime of 2, so the first derivative of our function at x equals 2, is equal to 8 for our final answer. So that you can kind of separate up the work and do it separately, but let's look at how we would do it all together in one big calculation here. So we want to find the equation of the tangent line. So we're fitting y equals mx plus b here for the equation of the tangent line. What we found up above here, how I could describe that f prime of 2 equals 8, I could say the slope of the tangent line to f of x at x equals 2 is 8. So that 8 was the slope of our tangent line at x equals 2 on this function. So what we're going to do here is pretty much the same steps, and that first derivative is going to give us our value for m. And then what we can do is use some extra steps to solve for b to make our complete equation of the line. But let's start with finding the slope. Actually, so let me go through a few notations here. So this f prime of 3, so we're looking for the first derivative at x equals 3. This is the same thing as finding that slope of the tangent line. So we're going to evaluate the limit as h approaches 0 from f of 3 plus h minus f of 3 all over h. Now, our function is x squared, so I'm looking at the limit as h approaches 0, and we're looking at x plus h squared minus, not x, 3. Sorry about that, 3. And then we're going to compare that to, or subtract 3 squared all over h. And when you're doing this, it's good. This doesn't make much of a difference in this example, but using parentheses there is a good habit to have in case you need to distribute that negative. So this is going to give us the limit as h approaches 0 of 9 plus 6h plus h squared minus 3 squared is 9 over h, which if we keep simplifying, will be the limit as h approaches 0 of h squared plus 6h over h, which will bring us to a limit as h approaches 0 of h plus 6. Plug in h equals 0, and we'll get a final answer of 6. So what that's giving me is if I want the equation of the tangent line, I'm at a point where I have y equals 6x, but I still don't know what my y-intercept is, so I still have a plus b, but we just found the slope of our tangent line. Now to find b, what we're going to do is go back to our original function up here, and we're looking at x equals 3, and our tangent line should be going through our function at that point, x equals 3. So if we think about our coordinate where x equals 3, our y-coordinate is 3 squared, which is 9. So this is a coordinate that we'd want to be using with our equation of the tangent line. So what we're going to do is plug in x equals 3 and y equals 9 and solve. So 9 equals 6 times 3 plus b, which is an 18 plus b. Subtract 18 from both sides for a negative 9. And that'll have us end with a y equals 6x minus 9. Real quickly, I'm going to show you how we can check our answer using Desmos, especially for this equation of the tangent line, because it shows up pretty nice graphically. So if we graph x squared, and then for clarity, we could go ahead and show the coordinate 3, 9, so we could see where are we calculating the tangent line. And then we just found the tangent line 6x minus 9. And what we should do is we should be getting a visual of a tangent line that is hitting right at that point and matching the slope. So that if I zoomed in, it basically looks linear with the two functions overlapping with each other. But if I zoom out, I could see it as a tangent line matching up at the slope just at that coordinate and only going through that coordinate.